All right, so first section we're going to take a look at is 9.1. This is on what we call parametric equations and graphs. And up until this point, all the graphs that we've done are y equals. Okay, that's function notation. Well, there's other types of graphing on the calculator. And if we take a look at the calculator up. All right, so if you take a look at the calculator when you go to mode, you'll see that there's a few different types of graphs. Okay. Function is the one that we've been using all along. And that's when you turn it on that mode, you press the y equals button, everything is in terms of y equals. Parametric and polar are two other types of graphing that you can do. Okay? And what they do is really give you different types of graphs you can draw. So we could draw something like that, which would definitely fail the vertical line test because it's not a function. So that's not something you can draw with y equals, unless you split it into multiple parts and you do every part of it separate. But we can draw all that with one single equation. And here's a couple other graphs. This one in the middle, that would be pretty complicated. Doable, but not something we're really going to spend a lot of time on. But the ones on the end we would look at. Those are a little bit simpler. All right, so let's take a look. First, just kind of define what a parametric equation is, how it works, and we'll get into doing some stuff on the calculator, and it'll be stuff you have not seen before. So first of all, when we're talking about parametric equations, we're talking about two functions. You need two functions to draw one picture. And if I put my calculator in parametric mode, you'll be able to see when I press y equals, it gives me two sets of equations for each graph. So there's four graphs you can see on the screen right here. The blue, the red, the black, and the purplish magenta one. Well, to graph something on the blue, there's two slots. There's an x and there's a y slot. You need two separate formulas when you do a parametric graph. And I'm going to call these two formulas f and g. And essentially what these two different formulas do is give you the x values and the y values separate. So that's a different idea that we've never really done that before. You have one formula that's going to generate the x value in your coordinate, and then you have a different formula that's going to generate the y value in your coordinate. So we're splitting the x and the y values into two formulas. Yeah?
Is that interval I or interval t underlined?
I.
Okay.
Yeah. So when we talk about an interval, it's like a domain. Okay? We're talking about a set of numbers that we're going to apply to these two formulas. Maybe your interval is 0 to 5, which means you're going to plug numbers into these two formulas, but the only numbers you can plug in are numbers between 0 and 5. So that's part of graphing something parametrically. They have to tell you the number or the interval they want you to sketch it on. And if you take all the ordered pairs that you get over that interval, so usually you have to plug in as many points as you need to get a good sketch. The number of points depends on the complexity of the picture. If you're graphing something that happens to be a straight line, well, then that's pretty simple. Couple points will do it. If you're graphing something that's like a spiral or something that maybe curves over itself, you might need a lot more points to get a good sketch. But when you plot all those points and actually make a sketch, we call that a curve, or a parametric curve. So these three graphs are all parametric curves. And the two formulas that you use to generate x values and the y values are called parametric equations. So you'll have one formula that's generating x values and another formula that's going to generate y values. Can't do it with only one formula. If you leave one of those blank, then that's trying to graph a coordinate like this. Well, you have to have a number there. You can't be missing a formula. You have to use both. And the variable that you use, or the letter that you use in the parametric equation, is called a parameter. So let's say I wanted you to find a point on a parametric curve, and I wanted you to do it for a parameter value of 3. What that would mean to do is take the number 3, plug it into your formula that gives you x, plug it into your formula that gives you y, and then write down the coordinate. So you're plugging the same parameter into both formulas. When you plug it into f, you get the x value, and when you plug it into g, you get the y value. And if you were going to do parametric in 3D, well, then you could have one more formula that's generating your z values. 3D parametric equations, it's not something we take a look at in this class. So we're going to spend a lot more time on it with the calculator, but the idea is if you need to change to parametric, you press the mode button, and then you highlight parametric, and then you hit enter. You don't have to change anything else. Right? Maybe radians or degrees. If you have a function that uses sine or cosine in it, then you'd have to deal with that. But that would be it. So all parametric curves are defined by a pair of equations. At least in 2D, a pair. And what you generally would say is the two equations that you're looking at parameterize or give you a parameterization of the curve. Basically what that means is the two equations give you a formula for this picture. But the fancy word for giving you a formula for it is a parametrization when you're dealing with parametric equations. Now I showed you on the first couple of graphs earlier, these parametric curves can be pretty complex. They can definitely intersect themselves. Not something you normally see with y equals. I mean, think of like logarithms, exponentials, square roots, a sine, a cosine, a tangent. None of those graphs cross back on themselves. But parametric ones definitely can. They can kind of circle back and cross over themselves. Now, what's a little bit different about a parametric equation, or the graph of a parametric equation, is it has a start and an end point. Right? It's not necessarily like the graph of sine that would go on forever. Right? Usually parametric equations start somewhere and they stop somewhere. Now, the start and stop point can be hard to see if they're the same. So maybe this graph starts here, goes this way, goes through these values, and ends there. So in that case, the start and the stop point are the same. But in some sketches, they might not be. So you might have a sketch that looks something like, I don't know, like that. And you can definitely see where it starts and stops because they're not the same point. And where the graph starts and stops depends on what values you plug in for the parameter. And this is where that interval is going to come in. So when they tell you you have a graph that's defined over a certain interval, let me just show you an example. This graph we're going to do. Here is the interval from 0 to 1. What this means is you are only allowed to plug in values for t in these two formulas that are between the numbers 0 and 1. So this is going to control where the graph starts and stops, because you're controlling the minimum value you can plug in for the t, and you're controlling the maximum value you can plug in for the t. So in general, I'm just going to say that I have an interval that goes from A to B. When you do an actual problem, the A and the B are numbers. If you want to find where the parametric equation starts, like if they just ask you to find the initial point of the parametric equation, you take the A value and you plug it into the formula that gives you the x, and then you plug it into the formula that gives you the y. So there's two calculations you have to do to find where the graph starts. One calculation for the x value and a separate calculation for the y. If you want to find where the graph ends, there's also two calculations you have to do, but you're going to plug in a different number. To figure out where a graph ends, you look at your interval, look at the maximum value in your interval, and you plug that number in to the formula for x, and then plug that number into the formula for y. So essentially there's 4 calculations you have to do to find where a graph starts and stops. All right, so let's try an example with some actual numbers, and I think that'll help it make more sense. Now, if you're graphing a line segment, figuring out where it starts and stops is perfect, because that's all you need. 2 dots, connect them, you're done. When you're graphing something more complicated, knowing where it starts and stops is good, but you may need a lot more points than that, especially if it curves and does other things. And that's where the calculator would help us out. All right, so let's go through this and look at what we have. First of all, this is a set of parametric equations. Relatively simple equations. Okay? 1 minus 2t and 2 minus t. 1 minus 2t is the formula that's going to give you the x's. 2 minus t is the formula that gives you the y's. Now, what I'm doing here is I am controlling what you can plug in for t. I'm not letting you plug in anything you want. I'm only allowing you to plug in numbers between 0 and 1. And there's a way to put this in on the calculator to tell it what values to use for the domain. And I'll show you how to do that. So let's find the endpoints of the curve. Okay, so I've got my 2 formulas. What value am I going to plug in for t to figure out where this curve starts? Okay.
0.
I'm going to plug in 0. Yep. So let's find the start point, which means you're going to plug 0 in to 1 minus 2t, and then you're going to plug 0 in to 2 minus t. So that's 1 minus 2 times 0. And plug it into y. So John, what's that going to give me for an x value when I do that out? 1. And Caleb, y value?
2.
2. So the start point of this parametric curve is 1, 2. All right. Now we want to figure out where it ends. And it isn't going to have an end. It's not going to go on forever, because t is not allowed to go on forever. We've restricted the domain to be between 0 and 1. Why between 0 and 1? That's just what they picked. You could do 0 to 6 if you want, but this problem is 0 to 1. Okay, so what are we going to plug in for t to figure out where this curve ends? Michael?
1.
1. So you're going to do x of 1 and y of 1. So 1 minus 2 times 1 and 2 minus 1, right? Yeah. So Sophie, what's my x value going to be? Negative 1. And Maddie, my y value? 1. So this graph is going to end at negative 1. 1. Any questions on finding those 2 points? Now, think about anytime we sketch something, and you probably haven't thought about it in a while, but when you sketch a graph on the calculator, what direction does it draw the graph in? Yeah?
From left to right.
It always is drawn from left to right. Right? If I just do zoom 7, it always goes left to right when you do function notation. It never has done anything else. But think about this one. Just a rough idea of your points. You're starting at the point 1, 2. That's the start. And you're finishing at the point negative 1, 1. Negative 1, 1. I'm not necessarily saying how you're going to get from the start to the end. Maybe it's straight, maybe it's a curve. But what direction are you heading as you go from the start to the finish?
Left.
You're heading left. So when I type this in on the calculator, it should draw it from right to left. It should not draw from left to right. All right, so let me type it in real quick just to show you. And we're going to do this several times, but probably good to kind of watch what I'm doing. So I'm putting it in parametric. If there's any equations in there, I'm just going to clear them out. And you need to type them in the same set. So this is one set of parametric equations. You can put them both there if you want, or you can put them both there. Okay, you need to use an x and a y from the same set. So let's put in, what is it? 1 minus 2t. Now, when you press what used to give you the x value, it's automatically going to put the t value. This button does 4 different variables depending on the mode. So now it's going to do a t. Don't want to use x for this. We always use t. And 2 minus t. Okay. Now, you are going to notice a couple of different things when you go to window. Anything there that looks new?
T's.
Yep, the t step. That's new. And what else?
Just it's not lines right there. Oh, there's a line.
Yeah, you still have a y min and max. Yeah.
T min and max.
You have a t min and max. Well, the t min and t max is your interval. This is the min. This is the max. So this is t max. That's t min. You have to type those numbers in as part of your window now. So we're going to put in 0 to 1. Well, for the x min, x max, y min, and y max, I mean, really, if you had a graph that did negative 3 to 3, that's going to be more than enough, I think, to see what's going to happen here. Because it is a straight line segment, so I know it's not going to go off the screen. So negative 3 to 3, negative 3 to 3. And now, this t step. So what t step does is it controls how many points the calculator is going to plot as it graphs from the start to the end. Right. Do you want to just do one in the middle and then connect them like that? Or do you want to get even more detail and maybe do bunch of points like that. Essentially what the calculator is going to do is it's going to do a bunch of points and it's just going to connect them all with straight line segments. The more points you have, the smaller those line segments will be. That starts to become important when you graph something that's curved. Because if you want to graph a circle, and let's say you only graph a limited amount of points like this. Well, parametrically, when your calculator draws that, it's going to look like this. If you wanted it to be more circular, you should have plotted more points to get more detail. So in this case, the step is set to 0.13. That means the calculator is going to use the following t values. It's going to start at 0. And the next one is going to add 0.13. That's the next t value that it would use. And it's going to plug that number in for the x, plug it in for the y, and plot a point. Then it's going to put in plus 0.26. Plug 0.26 in for the x, for the y, plot another point. Then it's going to do 0.39. And it's going to do 0.52, 0.65, 0.78, 0.91. And now, what's the t max? It's the highest that t can go.
1.
What is it?
1.
1. So it can't do another step. If it tries to, the next step is 1.04. That's not a value you're allowed to plug in because of what you restricted it to. So it's better to pick a t step that divides into your maximum. For example, going by 0.1 would be better. Because now you're going to get a point at 0, 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 0.9, and then 1. So try to pick a t-step value that lands on the t-max. Does that make sense? Yeah?
So it'd be anything between 0 and 1 that you put in the t step?
No, you can pick anything for the t-step. Any number. Problem is, like, if you pick a t-step of 5 here, well, then what the calculator would do is it would plug in 0 for your first point, and then it would say, okay, I'm going to add 5. So now I'm going to try to plug in 5. Well, you've already gone beyond the end of your t-max. So that's way too big of a step. So I'm going to hit graph and watch the direction that it graphs. It might do it kind of quick, but see if you can catch it. People see which way it drew? It drew it right to left. Now, if I put in 0.01, watch what happens now. How did the speed compare to the first time? Much slower. Because what the calculator is doing is it's graphing a point, or it's graphing every single point between 0 and 1, going by hundredths. So it's plugging in 0.01, getting a point. 0.02, getting a point. Probably more detail than you need for this sketch. Okay? And if you put in something like 0.001, now what it's doing is it's graphing every single point between 0 and 1, going by thousands. So you're plotting 1,000 points between the finish and the end and connecting them all. That's way too many points. And it finished. But if you do a complex enough graph, especially let's say your interval is 0 to 20, and you go by thousands, you're going to be graphing 20,000 points. It could take 20 minutes to do that. So if you get in a situation where, let's just make it so it would take a very long time to finish. Did I change the wrong thing? Maybe it didn't like how small I made that number. Okay, so anyway, that's going to take a very long time to graph. If you want to just stop it, just press second off, and the yellow circle will stop spinning. You can't do anything else until you press second off. So the goal here is basically to find a t-step that is enough detail for your picture, but not so much detail that it's going to take forever to sketch it. Any question on that? All right, so let's keep going. And let's take a look at an example where we can convert something that's parametric back to the type of equation that we're used to. Okay, y equals. So we're going to take that same problem we just did. But this time, I want to rewrite it as a y equals mx plus b. Now, I know I can do that because when I look at the graph, it's a nice straight line segment. I can easily calculate the slope of that, and I can find the y-intercept. So that is doable. If you have a complex enough parametric equation, that might not be doable. Like the one that looked like a butterfly, no, you're probably not going to be able to rewrite that in y equals mx plus b. Okay. It's too complicated. It's not a line, okay, so we can't do it. So let's look at example 1 again. Here's your formula for x. Here's your formula for y. The goal, when I'm done, is to end up with something like this. Particularly y equals mx plus b, because this is a straight line. If it wasn't a straight line, it might look like something else. But this one will look like y equals mx plus b. Anybody have a thought about how I can eliminate that parameter in the y equation? Somehow using the x equation. Yep?
Substitution.
Yeah, we're going to do substitution. That's what eliminating the parameter is. Right? Substitution. What letter are you going to solve that equation for? John? Yeah, we're going to solve it for t. Can you tell me the 2 steps, one at a time, to solve for t?
5 by 1.
Subtract 1.
Subtract. Yeah, and then was it divide?
And divide by -2. So what I'm going to do is I'm going to divide each part of that separately by -2. So that's gone. And x divided by -2 is really -1/2 x, kind of getting it ready for y equals mx plus b. And what's -1 divided by -2? 1/2. Okay, so we've solved the t equation. We've solved the x equation for t. That's step 1. And if you can't do that, you're stuck. So we were able to do it, so that's good. And now, plug that in for t. So we get y equals 2 minus, and now we're going to have to distribute that negative. -1/2 x plus 1/2. Right. Can someone tell me what would be my final answer in that box? Basically, I just want to know what the m and what the b would come out to. John?
Y equals x minus 1.
What's your slope again?
Just 1, because the 2 times the 1/2.
But that 2 is not distributed. Yep.
I got y is equal to 1/2 x plus 1.5.
So you're definitely going to get the 1/2 x. You have to distribute that negative. So that becomes a 1/2 x. And then you're going to distribute the negative again. That's -1/2. And you have a +2 out in front. So it becomes 2 minus 1/2. Excuse me. I guess if you wanted to keep it as a fraction, you could have done 3/2, or you could have made this 0.5. But that's your equation. Now, let's graph that and compare that to what we had originally. So here's the parametric version. Let's do the y equals version and see if they look the same. We should set the same window, -3 to 3, for an accurate comparison. What was it again? 0.5x plus 0.5x plus 1.5. And let's set our window. Actually, I think the window carries over. The x-min and x-max, they carry over no matter what mode you put it in. Okay. Do they look the same? No. Why? Okay. What? There's what? Yeah, when you do something parametrically, there's always a restriction on it. There's a start and there's an end. When you do something as a function, unless you specifically specify the domain, there isn't. Well, the domain here, if we go back and look at our graph, look at the start point and the end point. It started at the point 1, 2, and it ended at the point -1, 1. The domain was from here to here. So you should have only graphed between -1 and 1 to make it look like that one. So we can do that. We just have to put that condition in parentheses next to it. So next to it, you want to put x is less than or equal to 1, but it also has to be greater than or equal to -1. Second test for 1. All right, what did I do? Actually, you tell me. What did I do wrong? That's okay. I don't want a 0 in there. Yeah.
Was it -0.5? Oh, never mind.
No, the equation is fine. It's my condition. Yeah.
Your other thing's pointing in the wrong directions.
Well, I would just put a negative in there like that. Because you want x to be greater than or equal to -1 and less than +1. That's the best I can do. I know it's still drawing on the x-axis, but there's nothing I can do about that. So essentially, I get the same graph. In function notation, the calculator is going to try to draw everywhere. So just pretend like that part isn't there, and that's the best we can do. So part of eliminating the parameter is making sure you restrict the domain. So technically, what you need to add to the answer to this problem is this. That is just as much a part of the answer as the formula. You have to tell me where to draw it because of the original restriction. And this -1 and 1, that's the start and the end point x values. That's what we got. That's where we got those from. All right, so any question on how we eliminated the parameter or came up with that restriction on the domain? Let's try to eliminate the parameter here. This is not really important until you get to restricting the domain at the end. So we can come back to using this at the end. But what's my first step to eliminate the parameter? John?
Substitute, or sorry, like solve one equation for t.
And you have to solve a specific one.
X.
Yes, solve the x equation for t. So if we do that, what does t equal? X plus 1. Now, what do we do with that x plus 1? Yep, plug it into the y for t. So, our formula is going to be y equals, this time it's not going to be y equals mx plus b. This is not a line segment. Okay, so it's x plus 1 squared, or if you FOIL this out, can someone tell me what you get?
X squared plus 2x plus 1.
Yep. X squared plus 2x plus 1. So if you didn't put a restriction on it, what shape is that? A what? Yeah, it's a parabola. But we're going to be putting a restriction because we're not drawing an entire parabola. The original problem was only a small section, so this should only be a small section. So we have to figure out what that small section is. So focus on just the x one. If you plug in 0 for t, what do you get for a starting x value? -1. And if you plug in 3 for t, what do you get for an ending x value? What do you get?
9.
2.
2.
3 minus 1. Right? Any question on?
Oh crap, sorry.
Any question on why it's 2? There are a couple different answers there. We're just getting the starting and ending x value. So the starting x value is -1, and the ending x value is +2. So I can tell that this parabola is traveling from -1 to 2. That's the restriction on it. So you're getting a parabola, but you're only getting the section that's between -1 and 2 on the x-axis. And the reason it's greater than, or less than, or equal to is because this interval is brackets. I don't think they ever use parentheses with the interval. I think they always let you include it. So there's your answer. Any question on that? Okay, so what we just did is eliminating the parameter in order to get something that doesn't have a parameter is not always possible. There are equations that you can't solve for t. For example, this one. You're not going to be able to get t by itself in that equation. It's just not possible. The problem is you have a t as an exponent and a t as a term in front. If you got rid of one of those t's, then it would be easy. If you got rid of the first one, then you have a t as an exponent. We can use a logarithm to get the t out of the exponent. But a logarithm isn't going to help us with this t. Okay. So it's not always possible to solve an equation for t. But it is always possible to write something parametrically. And there's a very simple way to take something and make it parametric. So let me show you a kind of an idea, and I think you'll see how to do this. Let's say you had that equation. Anybody think of 2 equations I could write down so that when I eliminated the parameter, I got that as the answer? I'll give you a hint. One of these equations is going to be extremely simple. It's going to be the simplest kind of substitution you could basically do. Yep? Let's let x equal t. So let x equal t. So essentially, if you want to kind of look at it the way we were doing it before, this is how I wrote the equation. X equals t. And now, what could you let y equal? So when you did that substitution, you got 3x plus 2. Okay?
3t plus 2.
Yeah. That's the simplest way you can take anything and make it parametric. It's kind of a cheap way to do it, but it works. So basically, just let x equal t, and let y equal your original problem, but make your variable a t. Now if you do the substitution, well, the substitution says everywhere you see a t, you can substitute in an x. So if you do that, you get y equals 3x plus 2. So it's kind of a simple way, and there's an unlimited number of ways you could come up with a system of parametric equations to get that as the answer. Y equals 3x plus 2. But I think that's the easiest. So the idea is you just let x equal t every time, and then in your y equation, just take your original problem and change the variable to a t, and it'll work. All right, let's try this one. So I want to take this problem and rewrite it parametrically. So what would I let x equal? Yeah, just let x equal t. And how would I get my y equation?
T with 1 second, T with third, minus 8, T with second, plus 2.
Yeah, just change all the x's to t's. Now, if you do what we did in the last 2 problems ago, solve the x equation for t. Okay, already done. And everywhere you see a t, you can substitute in an x. And then you get 3x to the 4th, and so on. Okay, so any question on how you can take anything and make it parametric? It's not always possible to go the other way. If I ask you to eliminate the parameter, then it generally will be possible. It will be doable. I'm not going to tell you to eliminate the parameter in a problem you can't. All right, so let's think about how we could write the equation of a circle parametrically. And if you get confused about thinking of the entire circle, well, don't think of the whole circle. Start by just thinking of a single point on the circle. This point right here. If you were going to write that point as a coordinate, it has an x value and it has a y value. I need to think of those as 2 separate formulas. I need a formula to figure out how far to the right I go, and then I need a formula to figure out how far up I go. So what do you think I'm basically going to do in this diagram that we've done a lot? We're going to make a triangle. And remember, when you write a set of parametric equations, the parameter is the thing that's changing. It's the thing that you change and you plug that into your formula. What would change in this triangle to give me different xy coordinates? Yep. Well, we're in a fixed circle, so we can't change the size of the circle.
The angle.
The angle. The angle is your parameter in this problem. So we'll call this angle t. The angle of the triangle is the parameter. It's the thing that's changing. Okay, so we'll call this side x. Let's call this side r. We'll call this side y. And what trig function would we use to find x? Cosine. And what would the equation be? Cosine of what?
Cosine t
Yeah.
is equal to y over r.
We're finding which one again? X.
Oh, so that's the adjacent. So that would be x over r.
X over R. And now, let's get X by itself, and we'll have the first parametric equation we need. We'll have the one for X. So what does X equal?
R cosine.
R cosine of your parameter, which is t. I know we normally call it theta, but it's a parameter, so we're going to call it t. All right. Okay. And now, what do you think the formula for y is going to be?
R sine t.
R sine t. So there are my two parametric equations for a circle. Now there's one more thing you have to tell me. What values would the parameter have to be to get a full circle? Let's say in radians. Yeah?
Pi.
2 pi.
Just the single value pi?
So
Yeah?
2 pi.
Just that value? If you plug in a single value for t, you'll get a single point on the circle.
Oh, is it plus the,
We need
yeah,
start and stop for t.
0,
Okay, start at 0. Where should we end?
2 pi.
Yes. T has to go between, and you generally don't include the 2 pi because that's a repeat of 0. But t would go between 0 and 2 pi. Let's try it. Well, actually, you know what? We're gonna do an example with a number in a second. Let's find the equation at the origin with a radius of 2. Okay. What would be my x formula for a circle at the origin with a radius of 2?
2 cosine t.
2 cosine t. And what would be my y value?
2 sine t.
2 sine t. All right, so let's take that in. 2 cosine t. 2 sine. Oops. Make sure you go to parametric mode first. 2 cosine t. And 2 sine t. Okay, so we got our two equations. Now let's check our, well, let's leave it 0 to 1 and see what happens. 0 to 2 pi is 0 to 6.28. So I'm only going 0 to 1. So I don't get a whole circle. I'm only going from 0 to 1. If I want to get an entire circle, and let's set the tick marks on the x-axis to go by 1s. I think it'll be easier to see it's a circle if I go by 1s with the tick marks. Now, it's fine. It's going to draw that, but you're drawing way too many points here. You're going from 0 to 6.28, and you're going by hundreds. So you're graphing 628 points basically to draw that circle. That's too many. You could get just as good of a picture drawing a lot less points. Okay, but there's your circle. Now it is a circle. If you check the tick marks, you can see that it does go 2 units in every direction. But it's because of the fact that the screen is rectangular and it's not square. If you want to fix it so you can make it look square, you can always do zoom 7, or no, zoom 5, which will make it look proportional and not stretched. Now, let's go by point 1. If you go by point 1, you're going to graph basically 10 points for every integer. 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 1 is the next one. So you're graphing 10 points per integer, and you're going through 6 integers and a little bit more. So you're going to graph 60 points, plus you're going to get up to 6.2. The next one would be 6.3 if you're going by tenths. So you're not going to quite get a point at your T-max, which means you might see a very small gap right at the end. And if you look closely, there is a very small gap because our last point is 6.2, but that's fine. So I think when you did point 1 is the step, it came out just as good as the last one. I mean, it still looks pretty circular. Now, let's say you do, let's see, that's 2 pi, 0 to 2 pi. So let's go by pi. Well, now you're going to get a point at 0, 3.14, and 6.28. You're going to get 3 points to sketch this circle. Is that going to look like a circle? If you plot 3 points, you're basically going to get this one, and that one. So when you hit graph this time, that's all you get. It's connecting those 3 points. Now if we do, instead of pi, let's say we do pi over 2. But don't change your T-max. Let's go pi over 2 as my step. Pi divided by 2. Hold. Pi. 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 It's not what I'm pressing. Pi. Divided by 2. 2. So what happens this time is when you go by pi over 2's, you're getting a point at 0, 90, 180, 270, and the end point is at 360. So it connects those 4. So not enough points here to get a good sketch. Yeah?
My graph is only graphing like 3 points right at the beginning.
And you're in radians?
No.
Okay, if you want to do this in degrees, your T-max would have to go to 360. All right. And then I would say if you're going from 0 to 360, 360 is a pretty easy number to get a nice points. I would say go by 5s. Because think about if you go 0 to 360 counting by 5s, that's a decent amount of points. It'll look more circular. All right. Any question on that one? All right. So notice an example, the one we just did. The domain and the range of the circle were -2 to 2. Look at the sketch. Left 2, right 2, up 2, down 2. So the domain and the range are -2 to 2. But the domain for the parameter was 0 to 2 pi. If you don't go 0 to 2 pi with the parameter, you won't get a full circle. What if you go more than 2 pi? What do you think would happen? Yeah?
It'll keep going around.
It's going to keep going around. It's going to start to trace over itself. So let's say you go to 4 pi. Now, depending on how the calculator rounds, the next group of points that go around the same circle might be 1 pixel off because of rounding. So it could make the circle look bolder. It depends. We can check it real quick. Let's go by 0.05 for the T-step. Yes, I can see it making it look a little bolder. I don't know if you can really tell. But that's because all the points the second time around, because of rounding, were probably 1 pixel off from where they were the first time. Okay, but one thing I might ask you for on a test is, what is the parameter you need to sketch this image without tracing over it? So for a circle, 0 to 2 pi is all you need. All right, and Now, let's finish up by looking at a few sketches of graphs so you can kind of see what they look like and trying to find how to fit them on the screen. So whenever you're dealing with a sine and a cosine function, remember sine and cosine are periodic, which means once you've gone through a certain amount of values, you start going through the same values again. That ends up giving you a graph that repeats itself. So think about that. What does the graph of cosine have for a range? Like when you plug a value in for t, you always get a number between what? Caleb?
-1 and 1.
-1 and 1. So the part that I circled is always between -1 and 1, and so is this. Now, you're going to multiply the part that's circled by t. Let's think of it this way. I want to figure out kind of a min and a max for my x's. If this is always between -1 and 1, and this value in front is between 0 and 4 pi, can somebody tell me, if everything lined up just right, what the minimum value would be? All right, so what could potentially be the smallest value you ever get from that formula if everything lined up just right? Yep? No, you go smaller. You could get a smaller value than -1.
-4.
What?
Be 0.
Well, think about what's the smallest this could be? -1. And what if this was 4 pi in front?
Then you can have -4 pi.
Then I'd have a -4 pi if that lined up just right. So -4 pi would be the smallest value I would ever get in that red box. Now, what about the biggest value?
+4 pi.
+4 pi. So if everything lined up just right. So as far as an x min and an x max, let's do -4 pi to 4 pi. And what about t sine t? What would be my min and max for that? Same, because the same domain for sine is the same. So if everything lined up just right, this could be a -4 pi, and this could be a +4 pi. The parameter is 0 to 4 pi. Did I already type that in? Oh, I don't remember typing that. Oh, I did from the last problem. So 0 to 4 pi. Now, you've got to go from 0 to 12. I would say if you go by, I don't know, 0.5 is probably good enough. I think if you go from 0 to 12.5, counting by 0.5s, you're going to get 25 points. If it's not enough detail, I'll fix it. So we've got t cosine t and t sine t. I can see what it's supposed to be, but that's not quite a good sketch. It's supposed to be a spiral. Okay, I probably didn't set my t max small enough. Let's go by 0.1, and we can smooth that spiral out a little bit. That looks better. Much better. All right, so that would be a complete graph for that example. So what you'd have to write down is the t step, the x min, x max, y min, y max. So I need to know what you used as a step and what you used as a window. Any question on that one? So this is just getting used to graphing. You just practice it. All right, let's look at this one. What's the potentially the smallest value you could ever get out of that red box? So this is going to go between -1 and 1, and it's being multiplied by 5. So -5 would be the smallest. So let's set that. What would be the largest? 5. Doesn't matter what you let the parameter go between. That red box is always going to be between -5 and 5. Now, let's think about this one. There is an upper limit on t, 20.5. So the smallest value you could ever get, if everything lined up just right, is when you plug 20.5 in, multiply it by -1, or no, multiply it by 5, and then if the cosine came out to a -1, you could get -102.5. And the biggest value you could get would be +102.5. So let's do -110 to 110 on the y-axis and see what happens. -110 to 110. What's the parameter from 0 to 20.5? Going by 0.1 is perfect. You're going to plot a couple hundred points in that case, so that's fine. All right, so now we've got 5 sine t and 5t cosine t. 5t cosine t. All right, your graph. So there's that -110 to 110. It's not going beyond that. And it seems like the more we let the parameter get bigger, we're just going to get this same pattern of it kind of going left to right, but growing vertically as it does so. So it kind of looks like a watermelon or something like that.
Rugby ball.
Any question on it? All right, so it does take a little bit of practice to get used to and setting your parameter, because if you don't set things right, then you're going to notice things like this happening. And it's like, what? That's not right. So just be careful with your parameter, set your window, and then you'll get some good sketches. Let's see. All right, so that, actually, hold on, I think I can, what's that, 1, 3, 5, 7, 9, 11, 13, 50. Boy, I wrote that a long way. So 1 through 17 odd, and then 21, 22, 25, 26, and 29 to 33, that's also odd. All right, so we'll take a look at that tomorrow, and then start 9.2, and we're going to do that one over 2 days.